Okay, today what I'm going to do is I'm going to cover the topic of networking. So this is lecture six in the in my slide set. All right. So to begin with, let's talk about what is a network? What does it consist of? So let me just so let's go to this graphic right here, and the network consists of these switches that you see, the switches and routers. And it also includes the communication lines, the communication lines between that are connecting the switches, or that's connecting a switch to a router, or switch to an end system, a computer system. So the network consists of those things. And also in the end system, in the computer system, you have what's known as the network interface card, the NIC, for the purpose of connecting the computer to the network. And so these are the elements of the network, if you will. The network interface card, the communication medium, and the communication could be wired or it could be wireless as well. So the typical types of communication medium that we have is copper. That's one kind, copper cables or copper twisted pair. That's one kind of communication medium. Another kind is fiber optic. And the third kind is wireless. So just air transmission through the air. That's what a wireless network is. Okay, now just to begin with some basic definitions, there are two types of networks. One is the data network, and the data network is for the exchange of information between computers. So when you're transmitting a file from one computer to another, that file is going over the data network. You're using the data network to do that. The other network is the voice network. So when you pick up a phone in your office and you dial the number of your office colleague or friend and want to talk to them, well, that's happening through a completely different network. That's the voice network. And we'll see different switching architectures. The data network is what's known as a packet switch network, and the voice network is what's known as a circuit switch network. And I'll explain those terms in more detail. But just right now, I'm just doing a basic state setting, telling you about the different kinds of networks that there are. And it's more recognized that the IT department is actually responsible for both the data network and also the portion of the voice network that resides on the premises of the customer. So you have the PBX, the private branch exchange, you have the phones. So all equipment, all voice equipment that resides on site, that IT is also responsible for. So it's not just the data network. The data network gets all the attention because the data network is where all this cool technology has been focused, of high-speed switching and routing and whatnot. But the voice network is also part of responsibility of IT. So at the top level, we have the distinction between the data network and the voice network. Then when you look at the data network, there is another distinction. There are essentially two categories. There's the local area network, and there's the wide area network. There used to be a time when people talked about metropolitan area networks, but people don't talk too much about that these days. So everything outside of the building is the wide area network, the internet. And what's inside the building is the local area network. And the two main local area networks that one deals with, well, there's the Ethernet, and then there's Wi-Fi. So Ethernet uses actual physical medium. So you can have copper-based Ethernet, and you can have fiber optic-based Ethernet, or you may have no physical medium at all, which is Wi-Fi. So both of those are examples of local area networks, and the internet is the wide area network that we have these days. Okay, the internet. So it's simply a connection of routers. I mean, if you talk about the internet cloud, well, what is that internet cloud? Well, it's just routers connected together by transmission lines. And we'll see more specifically what the function of the router is. What is it actually doing? But the internet cloud simply looks like it's a bunch of routers connected with transmission lines. The other thing to recognize about the internet is that it is actually a collection of networks. So it's not a single network that is owned by a single business entity or a government. No, it's a whole collection of networks, and these all have their own independent owners. So they're ISPs, internet service providers. The job of internet service providers is to connect your office or your home to the internet. So that's what the internet service provider does. The internet service provider networks are themselves connected by what are known as backbone networks. Ethernet, this internet is really this jumble, this collection of networks. And so what do the routers do? So we've seen that this is the picture of what the internet looks like, and inside each of these clouds is routers connected by transmission lines. So what are the routers doing? The purpose of the routers is to steer the information. So you want to let's say download a file from some server in the internet. Well, that file is going to come through that internet cloud, and the routers are steering that file till it reaches your computer. So that's the purpose of the routers. But let's look at it more specifically in terms of exactly how that steering is happening. So you want to, let's say, you want to download a file from somewhere. The first question is, well, how is that file stored in that destination, in that source computer from which you want to get the file? How's the file stored? Well, in computers, everything is stored in terms of bits and bytes. So a bit is a 0 or 1, and a byte is a collection of 8 bits. So when you have a file on a computer, and let's say it's a text file, let's say it's my syllabus, which is nothing but a text file, and you want to download my syllabus from whatever server it's on in the University of Toledo's servers. It's on some server. You want to download my syllabus from there. Well, the first thing to recognize is that this syllabus is a text file, and a text file is just a bunch of characters. And so each of these characters is mapped to a sequence of 8 zeros and ones. And so this is also known as encoding the text. And one of the most popular standards for encoding text is ASCII encoding. So what ASCII encoding is doing is it's looking at each character, and it's actually the way it's storing it is it's mapping it into a set of 8 bits. A bit is a 0 or 1. So each character is going to have a distinct pattern of 8 zeros and ones. And 8 zeros and ones is what's. So the file, when we say a file has a size of 5 megabytes, essentially what we are saying is that I'm 5 million bytes in that file. And so the file is just a chunk of bytes, if you will, and the number of bytes is determined by what that size of the file is. Now, when you want to download a file from some source computer where the file resides, the file is not sent as a single chunk. So it's not sent as 5 million bytes, all together. No, what is done is that the file is broken up into smaller chunks called packets. So they're not going to send you that entire chunk of 5 million bytes at one shot, in one go. They're going to break it down into packets. A packet, the size of a packet typically has been around 576 bytes. So, you can do the math, a 5 meg file, well, each of them is going to get broken down into bytes. So there'll be several thousand, each of them is going to get broken down into packets. And a packet size typically has been 576 bytes. So that 5 meg file, you can do the math, is going to end up being several thousand packets. And it's these packets that are individually transmitted through that internet cloud. And when these packets reach the proper destination computer, so here is this person who's trying to download a file. Maybe this person is a student in my class. They're trying to download my syllabus from a server in the University of Toledo's data center. And so the syllabus, or whatever, how many bytes, the syllabus is not a very large sized file. But if you had a file with some images in it, that can certainly be a large file, and it's going to get broken up into packets. Each packet being 576 bytes, and then those packets are individually through the internet cloud. And once all the packets comprising a file, the proper destination computer, then those packets are reassembled. The packets are reassembled, and the file is recovered and then sent to the user. So the packet has this kind of a structure. There's a body to the packet, and then there's a header to the packet. So it's in the body of the packet that the chunk of the file, the chunk of the user file, is kept. So you got a 5 million byte file. Well, you're going to break it up into chunks. Each of those chunks will be carried in a packet. So the chunk of the user file is the body of the packet. And then there is a header of the packet to the packet. So here I'm kind of showing this in this picture here, where the body of the packet is these, the zeros and ones comprising, that information is being brought in from the file itself when you're packetizing that. So you're creating chunks of zeros and ones, and each of those chunks of zeros and ones are then placed in individual packets. So the first chunk will be placed in the first packet, the second chunk will be placed in the second packet, third chunk of the file in the third packet, and so on. Each of these chunks is going to have a header, and that's this black portion that you're seeing there. The header is also known as a protocol header, and it has what's known as protocol information. The protocol information is necessary for the functioning of the network. So network protocols basically determine how this network functions. And the routers and the switches are essentially looking at the protocol information that is there in the header of each packet. So the body of the packet is meant for the user. The routers and the switches are not concerned about what's in the body of the packet. They're concerned only about what's in the header, so that they can do their job of steering the packet to the right destination in a reliable, error-free manner. That's what a network is supposed to be doing. So the network packet, the analogy is that the network packet can be compared to a letter. So if you think about a letter going through the US postal system, well, the US postal system has the same job. A letter comes in, they have to send this letter to the proper destination. So how do they do that? Well, you have to have the address of the person the letter is addressed to. So the address of the person the letter is addressed to appears on the cover of the envelope. And also, if this letter is mishandled or has to be sent back to the sender, then the sender's address is also there. So the address of the person it's addressed to and the sender's address are both there on the envelope. So you can think about the network packet as having a body, which is the contents, which is what is inside the envelope, and the protocol header is the envelope with these key pieces of information, such as the address of the person the letter is supposed to go to, and also the sender's address. So a very similar thing happens in the computer network. Every computer has an address, just like residential addresses of people. Computers have addresses too. And these are referred to as IP addresses. So the IP address, the structure of an IP address is quite simple. It's 4 integers. So it's 4 integers separated by dots. So for example, right here, 16.2.20.44, that is an example of an IP address. And there are another IP address, 172.1.56.2. So let's say this is the IP address of the source. which means the source is the, and that file is going to then be broken up into small place. Each of those chunks are going to be placed in their packets, and then those packets will be sent to the destination. So the destination computer's IP address has to be there on that protocol header packet, on the protocol header of the packet. So this destination computer 16.2.20.44, this destination IP address is what the routers are looking at to steer the packet in the right direction. So the routers in the internet cloud, they're constantly looking at what is that destination IP address. And then they're essentially taking the packet that has come in from an incoming link and sending it out on an outgoing link in the direction of the destination computer. And every router is doing that. So the first router would do this. The first router that got the packet close to the source of the source of the information, well, they're going to look at the packet's destination IP, and then they would send it in that direction. So they would probably, the first router would probably send it in this direction. Then the next router would again look at the destination IP address and again send it in the direction of the destination computer. And so all these routers in the cloud are doing that until the packet finally reaches the destination computer. And this is happening for all the packets that are part of that file. And once all those packets reach the destination computer, the reassembly process happens, which means the recovery of the file from these packets, which is also referred to as reassembling the packets. That happens, and then the file is given to the person who wanted it. Now, the first thing about IP addresses is that, yes, the IP address defines a computer's address, much like the residential address defines where a person lives. But the thing is, IP addresses are not directly handled by the user. The user, so supposing you're trying to get my file from a Toledo server, you don't know what the IP address of that Toledo server is. Let's say I want to find something about the history of IBM, then I don't know what the web server where IBM's history resides. I don't know the IP address of that web server. What I know is I can type in www.ibm.com. I know that, but I don't know the IP address of the IBM web server. So what happens is that the user is always dealing with higher level addresses, such as here, a couple of examples: sales.google.com. That's the higher level address, name. Two things that are happening here. Computers have both a domain name and they have an IP address. The IP address is not something that the user remembers or deals with directly. The user is dealing with domain names. So if I want to find something from IBM, well, I'm going to type into my browser www.ibm.com. That is an example of a domain name. Sales.google.com, well, if I want to go to the sales department of Google and want to get some information from them, then it's reasonable that the sales department server may have a domain name such as sales.google.com. So since the user simply deals with domain names, there is also, as part of the functioning of the network, there are also what are known as domain name servers. So these domain name servers they translate the domain name, which the user knows, into the IP address, which the user does not know and does not care to know. So when you're sitting at your browser and you're typing in the domain name, then your browser is going to query the domain name server as to what is the IP address of this domain name. The domain comes back with that IP address, and then the browser can then send the request to the proper destination server. So the domain name the domain name server is integral to the functioning of the network. Okay, now let's come to more specifics on network protocols. So conceptually, the network protocols are what govern how this network is going to operate. The network protocols are what is ensuring that indeed messages and files can be transmitted reliably from the source to the destination computer. Another way of looking at network protocols is that in order for the network to operate, well, there are all kinds of messages exchanged between routers and switches, between routers and end computers. Now, these messages have to follow a standard format. And network protocols define what those standard formats are for these messages that are being exchanged on the network. Just like, if you think about, again, to sort of continue with the analogy of humans, and so if you think about, when humans converse, well, they have to use the same language. I mean, if one person is speaking Greek, the other person is speaking Russian, they're not going to be able to understand each other. So similarly, routers that are talking to each other and are talking to switches and are talking to end systems, all of those messages have to follow standard formats. And network protocols define what those standard formats are. Okay, now protocols. So if you think about, so now let's turn our focus more to the IP network, the internet, and how it works. Well, the internet requires 3 layers of protocols to work. So, and these 3 layers are generically, they're known as the link layer, the network layer, and the transport layer. So every entity, every router or switch or end system, computer system, laptop, has a protocol stack, because you need these 3 layers and they have to work in conjunction with each other. So, essentially what you need is a protocol stack. So every entity which is going to participate in communications on the internet has to have a protocol stack. The stack consists of these link, network, and transport protocols. Now, these names are generic, link, network, and transport. They're also specific names. So if you're looking at the internet per se, and that's the most important network that is out there, well, there are specific protocols that are used. So for the link layer, we have Ethernet networks, we have Wi-Fi networks. So Ethernet and Wi-Fi are actually examples of the link layer protocol that is being used in the internet. The network layer protocol, there's just one type of network layer protocol that is used in the internet. It's called the IP protocol. And the transport layer protocol that is used in the internet is called the TCP, or the transmission control protocol. Now let's talk about, well, why do we need 3 different protocols? Couldn't we have done with one of them? No, we could not, because the 3 different protocols are doing different things. So let's first talk about the link level protocol. So when these network packets are coming from, the source computer to whatever destination computer where they're needed, well, these files are traversing links. So each of these, so as you can see here, they're links that are connected. So if you focus on the middle ellipse here, you see 2 switches, and there's a link, a communications link that is connecting those 2 switches. Now, when a packet arising from one end of that link travels to the other end of that link, so it's arising at this source switch and it's traveling to that destination switch. So we are still talking, everything is inside. We're talking about this elliptical region here, and we are focusing simply on this particular one single transmission line that is connecting this switch to the other switch in that elliptical region. Well, what happens is that the packet that is traveling along that transmission line can get corrupted. So what happens is there's electromagnetic interference, or EMI, which can corrupt the packet. In other words, the bits can be changed because of EMI, because of electromagnetic interference. So a packet is a string of zeros and ones, but hey, you want those exact same zeros and ones that were being sent by the originating point of a communications line to be received at the destination point of the communications line. You want the same zeros and ones. Otherwise, information would have been corrupted, and ultimately the receiver at the very end of the transmission route, if you will, the entire route, the receiver is going to get a garbled message. Is going to get incorrect information. So you never want a packet that is being transmitted on a transmission line to get corrupted. You never want any zero to be changed to a one. Now, but it can happen. But because of EMI, because of electromagnetic interference that's going to be hitting this transmission line, it can happen. A zero can be changed to a one. So the purpose of the link level protocol is to detect that has happened. So it detects that the link level protocol has the intelligence in it to detect that a corruption of the packet has happened. And once it detects that, then the link level protocol at this switch, the destination end of this link, is going to send a request back to the originating end of that link and ask that switch to resend the packet. Because, hey, the packet has been corrupted. So the destination end of that transmission link is asking the originating end of that transmission link. So far we are focusing on exactly this single link that is in this elliptical region there. And we are focusing on exactly these two switches. So we're not talking about the whole transmission path. We're just talking about this one single link where the packet has been corrupted. So the receiving end of that destination link, the link level protocol at the receiving end of that destination link is going to detect that event of the packet being corrupted, and is going to ask the source end of that link to resend the packet. And the source end of that link is then going to resend the packet. And it'll resend it as many times as, now let's say that the second transmission, again, there was electromagnetic interference which hits the packet and the packet gets corrupted. Well, the receiving end of that transmission link is going to request the source end. So the receiving switch is going to request the source switch to resend the packet. And this will keep happening until you get a clear and clean and uncorrupted packet that has reached the destination end of just this link. Of course, it's very unlikely that if you have had one instance of electromagnetic interference, so electromagnetic interference occurs through things like lightning, or if that cable is close to some heavy machinery, which it can be if computers are there on computer networks are there in manufacturing plants as well. If it was close to some heavy machinery and you just started the machinery, that's a source of electromagnetic interference. But a lightning strike or a start of heavy machinery, well, that's not going to be followed. That's typically not followed very quickly by another lightning strike. Within seconds. So therefore, the chances are that the next packet will not be corrupted. So you don't really need several. The point I'm trying to make is that you don't really need, the link level protocol doesn't really need to ask for several retransmissions till it gets a clean and uncorrupted packet. Typically, it may be if packet got corrupted, the second transmission, the packet would not get corrupted because the same kind of event of EMI would not happen, electromagnetic interference. Okay, now this story of retransmission of packets on the link happens for each link in the entire path. So in this path here, if we are looking at this server on the right-hand end of this picture, and so the transmission path is actually the transmission path of a packet is going over several links. So there's this first link here, then it goes to this link, and then this link, and this link, and so on. I was just focusing on one particular link in that whole transmission path. But there are several links that the packet has to traverse from the source computer all the way to the destination computer. Now, each of those links, there's a protocol, there's the link level protocol stack at each. So So on each link, the protocol stack that is operating at each end of that link is going to detect if any packet has been corrupted, and it's going to ask for retransmission. So that is happening on each link that is traversing the entire path from the source to the destination computer. So what this means is that what the link layer protocol does, it makes the transmission path error-free. It makes the transmission path reliable. Error-free in the sense that if an error is introduced through electromagnetic interference or any other source, if the packet has been corrupted, the link layer protocol's job is to ensure that through retransmissions, a clean, uncorrupted packet does reach the other end of that transmission line. The focus is always on a single transmission line. But once you make one transmission line error-free or reliable, well, the link layer protocols are also operating on the next transmission line in the path, and then the next transmission line in the path. So each of those transmission lines are being made reliable through the link layer protocol, which means you get an end-to-end path that is reliable. So the link layer protocol's job is to ensure that information is not being corrupted as information moves through the network. Now, there are different types of nodes in the computer network. And so we should really first define what they are. So we have routers, switches, and end systems in a computer network. End systems are like your PCs, servers, laptops, tablets, even a smartphone is an end system. It has an IP address in it. And in addition to end systems, so the file transfers are happening between end systems. Somebody from sitting in front of their browser is viewing a web page on some server somewhere else, then that web page is being downloaded. It moves through the routers and switches all the way to the end system. So exchange of information is happening between end systems, and the routers and switches are there to essentially steer the information in the right direction so that it ultimately gets to the end system. The other two types of nodes are switches and routers. Each node on the computer network has a protocol stack, but it's not necessarily the case that they all have the same protocol stack, no. So end systems have the full three-layer transport, network, and link. And as we describe what happens in each of those layers, the reason becomes clearer as to why we need all these three layers in the end systems. But in the intermediate, in the routers and switches, there's no user there for whom this data is intended. The routers and switches, their role is merely to steer the packets to the right destinations. And the routers do this through looking at the network layer IP address. And that's why in the router, you have both the network layer and the link layer present. Now, when the packet has traversed the internet cloud and it has entered the customer premises, it has entered the router, the packet is now in the building, well, then it doesn't really need an IP address to steer it to the end system, because now it's now in a local area network. So there it only needs essentially a switch, and most likely it's an Ethernet switch, which will then steer the packet to the end system. So that's why we have the three-layer protocol stack in end systems. In the switches, we have the link layer stack. And in the routers, we have the network and link stack in the routers. Okay, now what layer? It's the next layer, the network layer. In the internet, the specific network layer that's being used is the internet protocol, the IP layer. The job of the IP layer is routing the packet. So it's we talked about steering the information through the cloud. That's exactly what the IP layer is doing. So the IP layer is looking at the network layer. is looking at the destination IP address and is then steering the packet in the right direction. So if you think about, any packet that's coming into any router in this huge cloud, well, it's coming in through some incoming link, and the router is then going to send it out on some outgoing link. It's going to do that. It's going to look at the destination IP address and then send it out on the outgoing link, which will take it closer to the destination computer. And every router on the network is doing that. So therefore, ultimately, slowly the network packet travels through the network. Every router is pushing that packet in the direction of the destination IP address. And so ultimately, the last router basically will send it to the end destination. And this architecture of the network is also known as packet switching. So the internet is also what's known as a packet switch network. The packet switching term comes from the fact that a packet, as I mentioned, the file is not transmitted as the whole file in one shot. It's broken down into packets. So that's where the term packet arises from. And the second part, switching. Switching arises from the fact that when a packet comes into a router from some incoming link, then the router is looking at the destination IP address and sending it on an outgoing link. So this is the switching that's happening. Thing coming in from a certain incoming link, then being switched and sent out on an outgoing link that takes the packet in the direction of the destination computer. That's where the switching aspect comes in. Now we're seeing that there are actually two versions of the IP protocol. The network layer protocol in the internet is called IP, but there are two different flavors of it. There's IPv4 and IPv6. Now, the reason why we need to move from IPv4, which is what is there mostly for the most part today, but we've been migrating and slowly migrating to IPv6. And this migration has been going on for actually more than a decade now. The reason for the migration is that we are running out of addresses when, with IPv4. So IPv4 defines the IP address to be 4 bytes. So it's 4 bytes long, an IP address. Whereas, there's so much computers and every kind of device that needs an IP address, laptops and tablets and everything needs an IP address, and it's all over the world. So the world is basically running out of address space when you consider IP addresses to be only 4 bytes long. So it's this problem that IP version 6 addresses. So here, IP addresses can be 16 bytes long. So you get a huge boost in the address space for IP addresses, and you can support any number of the planet can support any number of computing devices that it wants, given this huge address space where an IP address is 16 bytes long. And like I said, this IPv6 has been again around for a long time. It's been kind of on a slow motion migration to from IPv4 to IPv6, and over a number of years. Today we see that in the U.S. here's some data. U.S. about 30% of the computers use IPv6. When you consider the entire world, it's about 20%. So like I said, it's a slow migration. It's been going on for 10, 12 years, and this is the state of affairs today. But certainly, everybody recognizes that IP. If you talk about 4 bytes of IP address, then indeed the world is running out of IP addresses, and the salvation is going to come through IPv6. Now, the voice network, this is the telephone network. This does not operate according to packet switching. This operates according to circuit switching. So what that means is when you want to, when you pick up your phone and you want to talk to your friend somewhere else, maybe in some other city, well, you're going to pick up the phone, and then the PBX is going to recognize that, and it's going to then ask the central office switches. So the switches that the AT&Ts have on their premises, those are known as central office switches. The voice switch that a firm has on its premises is the PBX. But what's happening when a person picks up the phone is that a circuit is being established through this cloud of central office switches, the voice switches and the AT&Ts, and then through the PBX, through the destination PBX, till the destination PBX rings the phone of the recipient. And then the conversation between person A and person B takes place. So an entire circuit is being dedicated to this conversation. So this is a very different architecture than packet switching. Packet switching does not dedicate any resources to anything. Packets come in and they're sent down the internet. There's no dedication. There's no circuit being established, and that circuit remains in place for the duration of the conversation. That is the circuit switching architecture. The internet behaves according to a packet switching, where packets come in and the router just looks at the incoming, just looks at the destination packet, sends it out on an outgoing link that will take the packet in the direction of the destination computer. Okay, so we talked about the link level protocol. Their job is to make the link error-free, or I should say reliable. In other words, errors can occur, but through the retransmission process, you're ensuring that a clean packet does reach the other end of the link, and this is happening link by link by link. So the entire path from the destination computer to from the source computer to the destination computer becomes reliable. All right. Now, what is the purpose then of TCP layer, the transport layer? Well, remember we said that the packet, that the file is chunked up into packets, and the packets are sent down the network. Then when all the packets corresponding to a file reach the end system, the destination system, they're going to be reassembled. That reassembly process is done by the transmission control protocol. So, so that's why you need the transport layer, and the specific protocol that the internet uses for the transport layer is also known as the TCP, or the transmission control protocol. So that's the protocol used in the transport layer. I should make one clarification, which is that the book seems to imply that the reassembly is done at the network layer. That is not correct. That is not correct. So the wording is a bit ambiguous. It appears as though the book is trying to say it could be done at the network layer, but that is not right. The network layer is not doing reassembly of the packets to recover the file. The network layer is concerned with switching the packet at intermediate points while the packet is still in transit, is still moving through the cloud. So the network layer is not concerned with reassembling the packets and delivering it to the end user. That is going to happen only at the end system, where all the packets are going to be reassembled and the file recovered and delivered to the end user. So that's the job of the transmission control protocol, the TCP protocol. Okay, so we talked about the protocol stack comprising of the link level, network level, and transport protocol. Let's talk a bit more about the communication lines themselves. So the communication lines, the communication line is simply this black line that I'm showing here, connecting a router to another router. So these are the communication lines. This is for a wide area network. Well, for the local area network, well, this could be, if the local area network is an Ethernet, then this would be the communication medium. So we have to talk about, well, what is the medium of these communication lines? That affects, meaning, is it copper based, is it fiber optic, or is it just air? In other words, the network is a wireless network. Now that affects a very key parameter of the communication lines, which is known as bandwidth. So communication lines are characterized in terms of the bandwidth. The bandwidth is how many bits can you send through this communication line in 1 second. Um, if you look at historical Ethernet, traditional Ethernet, that had a bandwidth of about 10 megabits per second. So when I joined industry, the networks that we had at that time in the early 90s were 10 megabits per second Ethernets. So if you then wanted some speed that was higher than 10 megabits per second, then you have to go to fiber optic medium. And of course, the speed of Ethernet itself, copper-based Ethernet itself, has tremendously improved over the years, over the decades. So if the 10 megabits per second was the situation in the early 90s, well, we've had a lot of 100 megabits per second Ethernet for a long time. And now we also have gigabit per second Ethernet. 100 megabits per second Ethernet is also known as fast Ethernet. And then the 1 gigabit per second is just called gigabit Ethernet. So you've got Ethernet, fast Ethernet, gigabit Ethernet. So those are the three primary transmission speeds for copper-based Ethernet networks. Now, if you want even higher speed than that, then you can get fiber optic Ethernet. So here, it's still an Ethernet network. In other words, the protocol, the link layer protocol is still Ethernet, which is what makes it an Ethernet network. But if you chose fiber optic instead of copper, then you can push the speeds to 10 gigabits per second. Now, as I said, technology marches along, so you can get, these days, you can also get 10 gigabits per second copper-based Ethernet. But fiber optic will also give you the advantage of longer distances. So fiber optic's advantage over a metallic medium like copper is better performance and longer distances. So if longer distances is a concern, then you would try to go to fiber optic Ethernet. For example, if you have a campus situation where you want to connect all the buildings in a campus with a high speed Ethernet, then the distances are longer than the distances involved within a building. So if you're thinking of connecting a set of buildings together, as in a campus, in an office complex, then that's a place where you would tend to use fiber optic Ethernet as opposed to copper Ethernet. And also applications where you need to transmit a large number of bits. So if you think about, let's say, a radiologist's office, so radiology people are transmitting, X-rays. So any image, video images, they're very bit intensive. So if you're talking about, let's say, the kind of Ethernet you may want to put in a radiologist's office, that's a place where you may again consider fiber optic Ethernet because of the higher speeds. And also, if some of these offices are being connected together, maybe in a large hospital, different offices being connected together in a campus kind of situation, that's another area where you would tend to prefer fiber optic Ethernet over copper-based Ethernet. And then the third medium is air, wireless transmission. And like I said, even though the rule of thumb is that fiber optic more performance than copper more performance than wireless, well, there's also been tremendous advances in Wi-Fi networks, in wireless networks. And the march of technology you can see here as well. Wi-Fi was actually there since the time I entered industry. And then Wi-Fi was, this is going back to the early 90s. And the standard for Wi-Fi at that time was 802.11a. And so that gave you a speed of about 1 megabits per second. And its effective throughput was even below 1 megabits. So that was not really a very useful network because you're too bandwidth limited. but you can see, the march of time. Today we are today you have a lot of 802.11n and G, and that's 54 megabits and 300 megabits. And you also have some deployments of 802.11 AC, which is at 1.3 gigabits. So yes, although there's the rule of thumb of fiber optic being more offering better performance than copper and then wireless, but you can still make individual wireless networks with sophisticated electronics that'll go at very high speeds. Of course, you have to pay for that sophisticated electronics. So 802.11 AC networks are not cheap, but certainly the speeds on wireless networks can be very high in certain instances. When you come to the wide area, here is where fiber optics really comes into play. So even though you still have some, legacy technology takes a long time to be fully taken out of the environment, out of the system, if you will. But so you may have some legacy, copper technology still out there, but most of the communication links on the internet, they are fiber optic links. And so if you look at the next page, these are some of the speeds of communication links in the internet. And OC stands for optical carrier. This is indeed telling you that you're using fiber optic. And you can see there, these are all in gigabits. OC48, OC768. These are the types of communication links you'll see in the internet, and they're quite fast. But I also keep the copper links. I just list them here as a point of comparison, and because of the fact that, well, it takes a long time for technology to be replaced. I mean, for all technology to completely disappear. You always find there are some areas where there is the old technology. Just like on the local area network side, there still is 10 megabits per second Ethernet still out there. So it's not everything is 100 megabits per second fast Ethernet and gigabit Ethernet. You still find 10 megabits per second Ethernet out there. So today we are in the era of cloud and mobile computing. We talked about the 5 eras of digital computing, and so the present era is called cloud and mobile computing. Now, if you think about what has enabled mobile computing, the main thing there really is that wireless networks are now able to support the kind of performance we need so that we can, do reasonable types of computations and applications on our mobile devices like smartphones, like tablets and laptops. If you look at the cellular network, 3G and 4G have certainly enabled, different kinds of applications to be done on smartphones. And now we're in the stage of migrating to even higher speeds on cellular, such as 5G. And the 5G rollout was really supposed to happen in 2020. But obviously the coronavirus, hit everybody's plans in 2020. And so, but we are on track. So if you look at 2021 and you look at the deployment plans of 5G by the various wireless cellular networks, you would see that these plans are aggressive, and a lot of the 5G rollout we can expect to see in 2021. And 5G is really bringing mobile data performance on par with the kind of performance you see from Wi-Fi networks. So this is really going to be certainly a boost in terms of performance, and it's going to boost mobile computing further. And like I said, I think the indications are that a lot of the 5G roll-up will occur this year. Now, if you move from, and now one of the things is that the 5G is going to offer performance close to Wi-Fi. So if you look at Wi-Fi, well, Wi-Fi has been evolving over several decades. Actually, Wi-Fi was there when I entered industry back in 1993, and the Wi-Fi speeds were, uh, really less than 1 megabits per second at that time. And so we have come a very long way with Wi-Fi. There's a lot of, as you see, these performance standards. The protocol standard is called 802.11, and it has gone from A to B to G to N. And there's a lot of G, 802.11G out there, where the speeds are, 50 megabits per second and above. There's also some N out there, 802.11N. And we also see some deployment of 802.11ac, which really brings Wi-Fi to 1 gigabit per second speeds, which makes it basically comparable to a metallic high performance Ethernet network based on metallic media, such as copper. So even wireless networks will be able to offer speeds comparable to what you see on copper-based Ethernet. So it's really the performance of these, wireless communications that has led to mobile computing becoming a true reality. Now, I should mention, we should also take a look at. I don't want to leave you with the impression that all wireless networks can be pushed as high as 1.3 gig, which is the 802.11ac standard. No, there are. If you think about satellite links, so satellite links, where are they used? Well, they're used in ship-to-shore communications. So you're on a cruise. It's not a good idea to be in a cruise right now, but let's say if you are, then certainly you could. Those links are satellite-based links, and satellite-based links do not have that much performance, as you can see here. The uplink 256K, and the downlink is about 1 meg. So it's so here again you're seeing a kind of the other side of the picture as well, where wireless medium, particularly long haul, is not going to offer you that much performance. One also has Bluetooth. This is also there in the UPS, and this is really for connecting peripheral devices like optical mouse or optical keyboards to your PC. More interesting wireless technology really is RFID. So RFID is about the replacement of barcodes, which are scanned by hand to see what's the parcel, what's the identity of the parcel. That optical scanning done by hand is being replaced by RFID. So in RFID, what you're doing is, instead of fixing a paper tag with the barcode, instead of fixing a paper barcode tag on the parcel, you are fixing a small tag with some electronics inside it, which is sending out through the airwaves what the identity of the parcel is. So now, to do inventory taking, to determine what parcels you have in your inventory, Walmart doesn't have to send a person into the warehouse to do optical scanning, which is labor intensive, error prone. It can now, if these items in the inventory, if they had the RFID tags, they would be transmitting through the airways what the identity of that parcel is. And it would all be collected by an RFID reader. So the person can basically get immediate stock taking of the status of inventory in the warehouse. And similarly, shipments that are in transit, parcels that are in transit, again, you could, at any transit point, you could use your RFID reader to determine what items are in transit. Let's talk, and this is sort of the concluding topic in this lecture, which is the different types of traffic that we have on the internet. Well, there's everything from web browsing, which is where the internet started, basically, to the video traffic. Now, so everybody talks about, what is chewing up the bandwidth of the internet, because the internet is, it's constantly, it's a voracious thing. It constantly demands more and more bandwidth and faster switches. What's the source of that? Well, the primary source of that is the streaming video that's happening on the internet. So it's all the YouTube stuff that people are doing. So it's all the streaming video. That is, so this red segment here, this corresponds to the streaming video. And as you can see, this study was from 2008, 2013, but as you can see, the end of the time frame, it's this red segment that is dominating, that is chewing up most of the bandwidth of the internet. And this is arising from streaming video, YouTube and other sorts of applications like that. The next segment that is dominating is the blue segment, and this is basically peer-to-peer file sharing. So a lot of this traffic is actually also, illegal traffic, where you're downloading pirated stuff. Could be software, could be music, could be video as well. But again, that's bit-intensive traffic, and that's also chewing up a lot of bandwidth. The original internet traffic, like web browsing, it's really now part of this little green sliver, that green segment that you see there, and that's not very thick. It's becoming a thinner and thinner sliver of the whole of the aggregate traffic, because because most of the bits are being driven by video type of traffic. So we talked about web browsing, voice over IP. So in that sort of the green portion of the traffic, you have all other traffic. Some of that other traffic is increasing, some of it is not. Voice over IP is interesting. At one point, people thought that this would go up explosively, but it hasn't panned out that way. Right now, voice over IP is it's still there. It's an important component of all the traffic that's there on the internet. So for Skype and WhatsApp, those applications use voice over IP. So what's happening in voice over IP is that the voice signal is being packetized. And then the internet network, which is the packet switch network, those voice packets are being sent down the internet, which is the packet switch network. So that's why it's called voice over IP. The reason why at one point people thought that voice over IP was going to take off is because of internet telephony. People thought that everybody is going to have these internet phones. Vonage was the sort of the pioneering company in internet phones. They came up with a pretty good commercially attractive product, but it hasn't really taken off that much. Internet phones hasn't really taken off that much because really everything is centered around a smartphone. So so the internet phone as a crucial means of communication has not fulfilled its promise. Internet phone also uses voice over IP. VPN traffic, this is for the internet inherently is not a secure communications medium. So the internet inherently is not encrypting packets, which means, well, anybody who's sniffing packets on the internet, and there are plenty of people are doing that, they can see what communications are flowing on the internet because there is an encryption of the packets. Now, that's obviously not a state of affairs that companies like, because they want their, you're sending business communications to your business partner. You don't want just about anybody to look at it. So to make communication secure over the internet, the technology we use for that is called VPN, or virtual private networking. So essentially what VPN does, so you can form what's known as a VPN tunnel from a destination, from a source site to a destination site. So from the manufacturer to a business partner, to a supplier, they can create an internet tunnel. And then what's happening is that the packets being sent on that tunnel are encrypted. So unless you have the key to decrypt the packet, you won't be able to see what's in the packet. So therefore, this is giving you essentially it's simulating a private network. In a private network where other people, because the private networks, those communication lines are yours, other people cannot look at it unless they did some serious, they hacked into that communications line. But in normal course, a private network, the beauty of it is security, because other people cannot look at the transmissions happening in a private network. Well, the virtual private network offers you a similar capability by encrypting the packets that are traveling down the public internet. Search traffic. Now, this is of course quite interesting, and it is a portion of traffic that is increasing. As you can see, searches are certainly exploding, and you have a multiplicity of different search engines out there. I talked about the rise of AI. So what's happening is that AI technology is being coupled with searches, so that the results that one gets back when one issues a query for something, are more intelligent, if you will. So an AI-enabled search engine will give you results that are more targeted to what you're looking for, and not give you extraneous results. So that's why the web is also being so the web is evolving to what we call the semantic web. The semantic web meaning that queries, the semantics, the meaning of the query is being deciphered by the web, by the search engine, and you're getting back results that are, again, a lot more meaningful and pertinent to what you're looking for. So the web is kind of going through a transition. So the present era is called Web 3.0. So let's look at, well, why is it Web 3.0? What was Web 1.0 and 2.0? So Web 1.0 was really the web that we had in the 90s, where yes, the web was informational, it was transactional, but it didn't have the social media. So Web 2.0 brought in the social media into it. And again, there's debates as to exactly, well, what was the transition point between, what is the year in transition from Web 1.0 to 2.0? Well, obviously, social media has been there for a number of years, and although some of the early players in social media, like MySpace, did not really succeed, but Facebook did, and Facebook has been around for a large number of years. So you can say the Web 2.0 has been going on for 12 years or so. But now we are reaching the era of Web 3.0, and Web 3.0 is what is happening today, which is it's a confluence of both the mobile web and the semantic web. So we said, when you think about the eras of digital computing, we said from a digital computing standpoint, the current era is referred to as the era of mobile and cloud computing. So if you were to look at it from the standpoint of the web itself, so the goal is to make the web accessible from anywhere, no matter where you are, whether you're on the beach or you're in an office. The web should be ubiquitously accessible, which means the web is really a mobile web. You can take it with you. You can access it wherever you are. So that's a defining characteristic of the web as we are experiencing it today. And the other defining characteristic is this whole thing about the semantic web, which is that search engines and the semantic web is really being powered with AI, artificial intelligence. So searches are coming back with results that are much more targeted to what really you were searching for. So that's the evolution. I should also sort of mention the concept of net neutrality. And this was really part of Web 2.0, but it has certainly carried on, which is the fact that countries, if you want to, so Web 2.0 was about your generating, your ability to generate information, put that information on the web. So now the question becomes, well, is there types of information that the government would censor, would not allow you to put on the web? And so the United States follows net, which is that unless the information is really extremely, extremely objectionable, information about, pornography or, child pornography or terrorism or something like that. So that kind of information is banned, yes. But the United States doesn't ban, other types of information you can have. If you were, so it doesn't allow you to, it doesn't allow a web service provider, an internet service provider to censor information that its subscribers may want to put on the web. So if one person is, if you want to put up political views that are Republican, another person wants to put up political views that are Democratic, and so on. Well, none of that. The law allows them to do that. So the internet service providers cannot censor information. So this is known as net neutrality. Of course, net neutrality, it doesn't exist all across the world. No. In other parts of the world, if you look at China or other parts of the Middle East, Iran, the net neutrality is not there in those countries. So those countries indeed do censor information that people can put out on the web, but not. But the U.S. Has net neutrality. Okay, so that's pretty much what I really wanted to say on this chapter of networking.